Hello and welcome to another video. In this video we're going to be doing the third problem from yesterday's weekly contest, which is maximum number that sum of the prices is less than or equal to k. And we're going to skip the first one because it was an easy one, and we're going to skip the second one and do that later because the second and the fourth one are basically just the same problem with a tougher constraint, so we'll just solve the fourth one after this one. And this one you're given an integer k and an integer x. Consider S is the one index binary representation of an integer num. The price of a number num is the number of i's such that I mod x equals 0 and s is a set bit. Return the greatest integer num such that the sum of prices of all numbers 1 through num is less than or equal to k. Note that in the binary representation of a number, set bit is a bit of a value 1, and the binary representation of a number will be indexed from right to left. So if this is s, the 1 bit is here, and then the 2 bit is here, 3, 4, 5, and so on. So it's one index and it starts right to left. And so for this example, for k equals 9 and x equals 1, they kind of show you that these are all of the numbers. And for 1, basically you need to go through every single bit because you need to go through bits that I mod x equals 0. So like 1 mod 1 would equal 0, 2 mod 1 equals 0, 3 mod 1 equals 0, and so on. And the easier way to explain it is basically if x is 1, then you need to go through every bit. Then if like x is 2, you need to go through every other bit. If x is 3, you need to go through every third bit, and so on. So here basically they're asking for every number, the price of the number is equal to the number of bits that are 1. So for 1, the price would be 1. For 2, the price would be 1. For 3, the price would be 2. For 4, it would be 1. For 5, 2, and for 6, 2. And so the number of set bits total here is 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the first 6 numbers, the number of set bits is 9. So the price of the first 6 numbers is 9, so the answer is 6. In the second one, like I said, you're looking for every other bit now. So for example, and they kind of show you this, if your number is like 2, the bits you're looking for is every second bit starting from the right. So this one you ignore, then this one you look at, then like the next one you would ignore. Let's say your number is something like this. You would ignore this one, then you look at this one, and so on, right? It's every even bit. Yeah. Because it would be like if you number these bits, this would be the first bit, second bit, third bit, fourth bit, and every bit that is even would mod 2 be 0. So that's what you're looking for. So they kind of tell you this. The second bit of 2 and 3 is a set bit because for 2 it looks like this, for 3 it looks like this. So these are both set bits. And the sum of the prices is 2. And then for 6 and 7 it's also a set bit because for 6 it looks like 4, 2, this I believe. So this is 6. And then for 7 it looks like this. And the bits you care about is basically this bit and this bit. So for both of those, there's only one bit that's on, so the price is 1 for both of those. And then for 8 and 9, so 8 looks like this. And the bit you care about are this one and this one. So for 8, it's on, which makes the price 1. And for 9, it's like this. So this bit is on, and you care about these two. So both of those, the price is 1. 1, 4, and 5 don't have set bits that are on. So they basically go through all of this and they tell you, like, if you go through all of these things, then you're going to find the sum of the first 9 numbers is 6 because the sum of the prices of the first 10 numbers is 8. So kind of what you want to recognize is to restate this problem, you're looking for the biggest number where 1 through n set bits at the right locations add up to k or less, right? And if you look at k is really, really big. So you can't just like manually look through the numbers because for something like this, the result is going to be really big, right? So you basically realize, and the other thing, I guess, that makes it kind of like easy to, well, not easy, but intuitive to figure out what you got to do is basically when you have this condition and you go through your numbers, right? You go through your numbers increasing from like 1 to something. It'll just be like true, 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 and at some point it'll start being false. And for everything bigger, it'll be false. So if you've seen this before, and this is pretty common, this is the kind of thing that when you see you'd want to do a binary search, because you would basically, ideally, for a number, just put in some number, you'd say like, okay, it's the sum of the bits from 1 to the number less than or equal to k. If it is, let me store it. Like in this case, it's too big, so I'd want to go left. But let's say you were over here, you'd say like, okay, this is fine, so I'd want to store it, and then I'd want to go right. And you keep doing this, and you can basically binary search through a lot of numbers and find your answer. But now this is the hard part, right? Like, how do you do that? Like, given a number, that's basically the problem. Given the number, like let's say you're given 20 and x is like 1 or something, figure out like how many total set bits are there, and you have to be able to do that pretty quickly, right? You can't like go through every number. You have to be able to do it in like like 1 or log time. So log would be fine as well, right? Like if you have some number that's some bits, let's say, I don't know, like this is your number, let's say, or like this. You are allowed to like go through the bits because this can't be too big, right? Like maybe there's like 20 or 30 bits max, which would be fine. So then you'd have, you know, your time complexity would be like 20 log of whatever this max number has to be. Let's say like 10 to the 15th or something, even like that would be totally fine. But you can't manually go through 10 to the 15 numbers or whatever you need over here. So the easiest way to do that, when you're not sure how to figure out something, like you're trying to figure out something and you're trying to see, can I do it quickly? The easiest way to do that for most problems is to just like draw out the first few numbers, however many it takes, to see if you could find a pattern. And once you can find a pattern, then figure out how you can do it quicker. So here we have some numbers. And so if we can actually look at one bit at a time and see if we can find any patterns. So you can see for like this last bit, this one bit, because it's one indexed, and right, so this would be like x equals 1 for the last one. It goes like 1 0 1 0 1 0 1 0, and that makes sense, right? Because every odd number has a 1 and every even number has a 0. Then over here it is 0 1 1 0 0 1 1 0 0 1 1. So there's kind of a pattern, but it's like not super clear. Like yes, there are alternating ones and zeros, but why is there only 1 0 here and then 2 1s? And then here there are 3 zeros and then 4 1s, 4 zeros, 4 1s, and so on. So it's kind of weird. Also, why are there 3 and then 4 instead of alternating? And here there's 7 and then 8 ones, and then it would keep doing that. So the easiest way to do that I noticed, to add a number, and this makes it very clear what the pattern is if you actually just, I wonder if I can actually go up here. I can just do this. So if you actually add 0, then the pattern is really clear, right? So if we look again, it's 0 1 0 1 0 1 0 1 0 1. So it starts with a 0 and it's alternating every single bit. Then here it starts with a 0 and it's alternating every 2 bits. Then here it starts with a 0 and it's alternating every 4 bits, and then every 8 bits, right? So as a general case, we can say starts with a 0 and then alternate every 2 to the so if we do keep this one indexed, then it would be 2 to the like if this was the actual index, it would be like 2 to the x minus 1 bit, right? Yeah. So basically, if the, like, yeah, this would alternate every 2 to the 0 bits. This would alternate every 2 to the 1 bits. This would alternate every 2 to the 2 bits, every 2 to the 3 bits, and so on. And notice that there are groups of numbers that are exactly the same. For example, here, right, there's like the 0 1 keeps repeating. So basically what you need to do is you need to, given some x, like if x is 1, you basically need to do this for every single bit. But so this would actually, instead of be like x minus 1, maybe we can rename this to like position or something, or I minus 1. And like I said, this I is 1 indexed in this case, not 0 indexed. If it was 0 indexed, it would be 2 to the I. So if x is 1, you'd have to go through every single one of these because every single one of these mod x is 0, right? So like 1 mod 1 is 0, 2 mod 1 0, 3 mod 1 0, 4 mod 1 0. If x was 2, then you'd have to go through every second bit because 1 mod 2. Or let's actually go back up here to see this. So here it is, I mod x equals 0. So if I is 1, I mod 2 is not 0, right? 1 mod 2 is 1, 2 mod 2 is 0, 3 mod 2 is not, 4 mod 2 is. So you basically start at the 1 index x bit, and then you add x bits until you get to like the number, right? So if x was 3, you'd go through every third bit. If x was 4, you'd go through every fourth bit, and so on. But basically, once you recognize that there's this like repeating pattern, let's just take a number like 16, right? So we're given 16. We need to figure out, and x is, let's say x is 1 in this case, just so we can go through all the bits and show. So how many total set bits are there for 16? Well, you'd basically figure out like how many total cycles are there for each of these things, right? So for this 1, a cycle is 2 numbers, right? And the easiest way to do this is because like if you start with 0, then this loops perfectly, right? Like you have a full cycle, full cycle, full cycle, full cycle. Where if you start at 1, it starts at like a half cycle. So when we're looking for 17, or we're looking for 16, the trick we can do is we can actually look for 17 instead, and that would kind of make it easier. So we're going to do 17, and then we're going to look for cycles because we're including this 0, right? If we start with 16 and we just start at 1, then we're not going to include it, but we can start at 17, and then that'll actually have full cycles. So what we can do here is we can basically figure out like, and this makes total sense, right? Because you see for 16, this is the start of a new cycle over here, right? It's like 1 cycle, 2, 3, 4, 5, 6, 7, 8 for this bit, and then there's a new cycle. So if we actually use this number and we mod it by the stuff we need, we're going to get correct numbers. So the first thing you take is you take your number, add 1, just so you can have these like correct cycles, right? Now, the next thing is you want to figure out how big is your cycle for each bit. So for the last bit, the cycle is 2, right? So for last bit, cycle length is 2. For second to last, cycle length is 4, and then 8, and so on, right? So basically, we want to figure out how many cycles did we go through, right? We want to calculate this in 2 parts. 1, complete cycles over 2, and then second part, so we can write this like 1, and 2 is going to be leftover region. So for 16, for this 1 bit here, like let's just do this bit here, how many full cycles did we go through? Well, like I said, it's going to work out easier if you add 1 and then mod 2, because the cycle for 1 bit is just 2. So how many cycles did we go through? And we can write this down for all these bits. So we can say like 1 bit, 2 bit, 3 bit, 4 bit. So for the 1 bit, we have 8 complete cycles, right? So let's write that. And the reason is because it's 17 mod 2, cycle length is 2, and where we have 17, we added 1 because we want to include the 0. So this is 8 full cycles. Now we want to figure out how the leftover region works. So like, right, like we have some part of a cycle left. We can figure out how much that is because we can just take whatever number we have minus our cycles. So we have 1 extra, and then we can figure out how the rest of the cycle works. So every cycle length, like if we just say cycle length n is going to have n over 2 zeros and then n over 2 ones. So you could see, like, for example, if we look at this one, this last bit over here, the cycle is 16, is length 16, right? It's this whole thing. And it'll actually make it easier. Let's actually look at the second to last one, because then you can see a bunch of these cycles, right? So each cycle here is length 8, right? It's 4 zeros and then 4 ones, and then 4 zeros and then 4 ones, and so on. So we basically have to figure out the leftover region and then the length of the cycle. And then we have to figure out how many zeros are there. So for example, if the leftover region is less than or equal to half the cycle, then we have 0 ones, right? Because the first half of the cycle is all zeros, so if the leftover region is less than or equal to half the cycle, then we have 0 ones. And basically the number of ones is however many we have after we subtract half the cycle from whatever we have left. So let's kind of walk through that. So in this case, the leftover region here is just 1, right? So we can write that down here. Actually, let's do this. Okay, so we have 1 left over. And because half of a cycle of length 2 is 1, if you have 1 left over, you won't have any 1s, right? Because it's going to be 0 and then 1. So how many total 1s do we have in here? Well, we have 8 full cycles. And how many 1s are in each cycle? So the number of 1s in each cycle is just half the length of the cycle. And the for the first bit, the cycle is just length 2, right? 0, 1, 0, 1, 0, 1. So if we have 8 full cycles, we have 8 1s total. And if we actually look, we do have 8 1s, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's go to the next one. So for the next one, what's our cycle length? So our cycle length is 4, right? Because it's 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So we have 17 numbers, and we need to mod it by 4. So we have 4 full cycles. And how much do we have left over this time? So we have 1 left over again, right? You basically, so this is actually not, this is not mod, this is divide. And then to get the leftover region, then you mod it. So we have 4 full cycles, we have 1 left over. Now, how long is the length of the cycle? The length is 4. So if we have 1 left over, it's going to be 2 zeros and then 2 1s. So this 1 left over will just be a 0. So the 1 left over doesn't contribute to the 1s. And there are 4 cycles with 2 1s each, right? So this is also 8 1s. Then we go to the next one. And here the cycle length is 8. So 17 divided by 8. So we have 2 full cycles, 1 left over. And this worked out kind of nicely just because I picked 16, but if I picked some other number, it wouldn't work like this. So that's why you have to do all of these one at a time. So here we have 2 full cycles and 1 left over, and the cycle is length 8. So each cycle is going to have 4 1s. So we'll have 8 1s in here as well. And we will have 1 left over, but since the cycle is length 8, it's going to be 4 zeros and then 4 1s, so we don't have any 1s there. And then finally for the last one, the cycle length is 16. So 17 mod 8 or 16 is going to be 1. So we have 1 full cycle, and we have 1 left over again. Just because, like I said, I picked 16, so it kind of worked out. I picked like a multiple of 2. So here it's going to be the same thing, right? Because the cycle is 16 and half of it is 1, so we'll have 8 1s. And then in this leftover region, because it's less than half the cycle, it's going to be no 1s. So here there should be 32 1s total. And we can quickly count it up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Okay, so looking at this, we actually made a small mistake. So 16 isn't this, this is 8. So 16 is actually this. So basically, if we can make it go, let's see here. I guess it doesn't matter too much. So basically, we have 1 more bit left, right? We have this like 5th bit. So in the 5th bit, what's going to happen here? I know what we can do. So we can just add zeros like this. It'll be kind of messy, that's fine. Yeah, it's a small error there. So basically, we have 1 last number left here. So let's look at that. So this is the 5th bit. So the cycle here is 1, 2, 3, 4, 5, 6, 7, 8. It is 32, basically, right? It's going to be twice as big again. So if we do this part, then, so it actually doesn't work out perfectly. So this is a good example. So if we do this part here, this is going to be 17, 4 divided by 32, which is 0 full cycles, right, for 16. And now how much do you have left over? We have this whole thing left over, right? So you have 17 left over. And so since the cycle is length 32, like I said, the first 16 are zeros. So how many extra do we have? We have 1 extra, so we'll have 1 1 here, right? Because if you have 17 left over, it'll be 0 16 times, and then the rest of it will be 1s. So you should have 33 ones. That's why it's 33. And so that's basically how you do that. And you can do this for other x's. So if x wasn't 1, like let's say x was 3, you would just start at this location here. And then your step, like basically what you would do is you would just keep multiplying your number by 2 to the 3 to go to the next like third one, right? So let's say your first number that you start is at, if it's at this location, let's say that's like 4 or something. You would basically just multiply by 8, then multiply by 8, then multiply by 8. And you keep doing that until you get to the actual number you were checking. So in our case, it was 16, but it can be something really big. So that's how you would do that. And then if it was by 1, then you would just always just multiply by 2, right? So you'd start at this first index here, then you'd multiply by 2, multiply by 2, multiply by 2 until you're basically checking every single bit until the bit is too big for your number, right? So you're basically checking like, is this number bigger than the number I'm looking for? And so on. And yeah, that's pretty much it. So we can take a look at the code. So here I made a function, like I said, that basically takes a number and checks if all the numbers below that are less than or equal to k. And first you add 1 because of the 0. Then you have all the total numbers. And you start at the power of 2 to the x minus 1. So for example, if x was 1, you want to start at 1 here, right? You want to start at the number 1. Yeah. And then you'd want to go to like 1, then you'd want to go to 2, then you'd want to go to 4, and so on. Because the number 1 is 2 to the 0. Because even though here this is 1 indexed, this actual value is 2 to the 0, 2 to the 1, and so on. So you start there, and you basically just say until the current number you have is less than x minus 1, or whatever number you started with, right? Because we added 1 before. Then you just get this like full and extra. So the full is basically how many full cycles do we have, right? Which is just this. So you take the number that you have minus the length of, or divided by the length of a cycle, which is just the power over the power times 2, because our power here is 0 indexed in this equation, right? So for example, if power equals 1, then the cycle is length 2. So you just say like, okay, well, how many full cycles do I have? And then I multiply that by this, which is half of a cycle, right? So if a cycle is 2, this will be 1. If a cycle is 4, this will be 2, and so on. So that will tell you how many full ones you have. And then the last part is how many extra ones do you have? So you just mod it, figure out how many extra ones you have. And then, like I said, this power is half of a cycle. So for example, if you have 17 left over and a cycle is 32, this will be 16. So then you'll have 1 left over. And this can also be negative. So I just did it like this, right? Because let's say I have 5 ones left over and half of a cycle is 16, then I'll get negative 11, which means that I have no ones left over. So that's basically what you do. You figure out how many cycles you have, how many extra numbers you have, add it together, and then just check the next number, right? So you just multiply your number by 2 to the x to jump whatever you need. So if you're checking like every 8th bit or something, you would just keep multiplying by 2 to the 8th. Then you just return, is your total less than or equal to k? And then so for these start and end bounds, it's a little bit tricky to figure out like what they should be. And basically you can just try like a really big number. But if you have something like k equals, let's say even k equals 1 and x equals like 8, or like, yeah, like 8. So 8 is going to be like 2 to the 7th or something. So you need your number to be pretty big. So you can't just like go from 1 to k or something. Because if you do 2 to the 7th, that's going to be like, I don't know for sure, like 140 or whatever it is. You basically have to like try a bunch of numbers. Like I said, you can just put in like 10 to the 15th here, but this also works, right? So 2 to the x will ensure that if k is small and x is big, it'll still be big enough. And if k is big and x is small, it'll still be big enough. So this kind of worked out for me. There might be some like better things to pick here. But like I said, you can't just arbitrarily pick, especially in Python, you can just pick something huge because the constraints are very easy to pass if it's logarithmic. You can do like 10 to the 20th or something as your right constraint. Well, that'll be totally fine. And then this is just the basic binary search from here and just calls this function. And so we can run it. And yeah, you can see it's pretty good. So for the time and space, so basically you're looping from like log of this. So this will be like log of k times 2 to the x. Like I said, you can just pick some huge value. And then for every single comparison, you're looping through the bits of 1 to k, and then it's going to be not quite 1 to k because it has to be a power of x. So it's more like log k over x or something like that. Something along these lines, right? Because like if k is like 30 bits or something and x is like 8, you're only going to check like 3 or 4 bits, right? You're going to check like the 8th bit, the 16th bit, the 24th bit, and so on. So a little tricky. Maybe this is like a little off, but that's basically how you do it. And yeah, so for these types of problems, from the constraints, it should be like reasonably straightforward that it's a binary search. If you know that like once your number is big enough, it'll always fail. And then what I would recommend for a lot of these problems where you don't know where to start, just write down the first few numbers and see if you can get a pattern. And once you can get a pattern, then figure out like, okay, now that I can kind of see it, how do I actually calculate it? And then that should be, yeah. And it's not super easy, obviously, but yeah, that's how I'd recommend doing these. And yeah, it's going to be all for this one, so hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.